Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Matthew Hopkins with us today. Hello, Matthew.
Hello,
Matthew, what's your geolocation? Where are you at?
I'm in Christchurch, New Zealand. I moved here 2 weeks ago.
Oh my goodness. Wow. All right. This is also the first video we got where we're going to New Zealand. So this is awesome. Very cool. And what takes you down to New Zealand? Do you live there?
No,
I mean,
I'm
is
from
that
the
where you're
UK.
from?
I'm from the UK. I did my PhD in the UK, but I've just started a fellowship postdoc here at the University of Canterbury.
Very cool. Very cool. And is the current weather in New Zealand anything like it is in the UK?
Surprisingly so, yeah, I'm quite disappointed. I was hoping to escape to beautiful sunshine, but we've had a lot of rain and a lot of wind.
You
How
just,
how is it in Arizona? Go on, make me jealous.
I think you just flipped the sign on the latitude or something like that.
Yeah.
No. Let's see. Currently, it is October 13th of 2025 as we record this. And in Phoenix, Arizona, we are definitely transitioning into fall. And in fact, it's been very unusual the last 4 days. There was a hurricane
Oh no.
off the coast of California and Mexico. And so it's come up. And so for the last 4 or 5 days, we've just been deluged with rain, which is completely unusual in the desert. So yeah, we are transitioning into fall in a wet way. Very good. And Matthew, what do you like to do for research?
So I mainly do interstellar objects, which is what we're
Cool.
talking about today.
Yes.
But that topic takes me to galaxy physics, to planetary physics, and I've even managed to link it to some radio phenomena as well. I like wacky ideas.
Interstellar objects are not so wacky these days.
Uh, we've
Definitely.
got a data set of three now. It's amazing.
Absolutely. Yeah, you can draw more than a line. Very cool. And that is going to take us to this very awesome APJ letter. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. From a different star, Three-Eye Atlas in the context of the Ōtautahi Oxford Interstellar Object Population Model. And Matthew, take us away.
All right. First of all, I'd just like to thank all the long list of co-authors you see there for this work. Rosemary also just finished her PhD
Oh,
here at the University of Canterbury, and we managed to swap hemispheres. She is now
oh
in
my
the
goodness.
University of
Wow.
Helsinki.
That's great.
Uh, John and Braden are both, and Michelle are all also here at the UC.
Mm-hmm.
And Michelle and Chris were my PhD supervisors.
Aha.
Uh, Hence the Ōtautahi, which is the Te Reo Maori name for Christchurch,
Yep.
Oxford,
Yep.
ISO population model. There's the
Very
link.
cool. Very cool. Good shout out. Good shout out. Okay,
This,
let's go ahead and get
yeah.
into it.
So we wrote this paper in the 3 days after Three-Eye Atlas was discovered.
Cool.
Um, with it was a lightning fast turnaround with kind of 24-hour work on it between the UK and Christchurch. Um, with with the discovery on I think the 1st of July, and us following
Yeah.
through, and then the kind of next few days.
Mhm.
Um, the reason we're able to do this so fast is because, as the title says, we were putting this object and the little that we knew about it so far into the context of the work that we'd already done building this population model.
Very
This
cool.
tells us what we were kind of expecting to see in ISOs. So we were plotting it on our graphs, seeing how it was different to what we thought, how it was the same,
Hmm.
and inferring all that we could from it.
Nice. And of course, this is a
um,
rapidly moving field, so we will
yes,
thing to see.
yeah. I made a joke about having three data points now. That's what the three in Three-Eye Atlas stands for. Atlas being the survey that found it.
Yes.
Um, the first was One Eye Oumuamua in 2017. The second, Two Eye Borisov in 2019.
Uh-huh.
So there's been a bit of a gap here before getting the third.
Hmm.
During which time I managed to start and end my PhD studying these things.
Good, good.
So I've been very excited for this moment for 4 years now.
Awesome. And may you have many
Um,
more happy moments coming soon.
that's Well, we'll get to that. um, One eye, two eye was the kind of observational context for three eye. One eye was a very small, non-active object. It didn't have a big cometary coma around it, which is what two eye had, and what we expected most ISOs to have. Three eye is very much following in Borisov's footsteps. It's again a comet. Since we wrote this paper, it's gone further into the solar system, and we've got more observational data on it, and we can really see it's blowing up and its comas. We've detected a whole host of molecules in there now, carbon monoxide and I think ammonia and cyanide as well, I'm pretty sure. A lot of things. These objects are flying, they are like asteroids and comets, but unlike all the other asteroids and comets that we see, which formed in the solar system and have stayed in the solar system their entire lives, these interstellar objects come in from outside. They formed around another star, potentially on the other side of the galaxy, potentially a star that's now actually long gone and died. So these objects are the main kind of interest to us, and what makes them absolutely fascinating is the fact that they formed from different material. They formed in another part of the galaxy in another time when the galaxy looked very different. So there's a whole heap of information packed into a very small sample of objects. But by studying them, we hope to be able to test our understanding of planet formation, our understanding of the galaxy, and everything on every scale in between.
Yeah, it's a huge wealth of really interesting stuff from another solar system. It's amazing.
Yeah. Right here for us to study. It's absolutely fascinating. I love it. Most ISOs we think form like asteroids and comets here, but then get ejected from the planetary system. It turns out that actually forming planetary systems is really messy. Something like 90% of the small bodies in our own system got completely ejected. And we suspect most systems are like this as well. So galactic space is littered with these small bodies. There are more of them out there than there are in solar systems.
Interesting. Great.
Yeah. So yeah, that's one eye, two eye, and then we found three eye. So we can go down to methods now, I think.
Okay. All right. Got that. I got okay.
Yeah.
Yes.
So this context of the Ōtautahi Oxford model that we're talking about is work that me and my collaborators have built up over the last couple of years. We're trying to predict what the ISO population looks like before we've actually seen that many of them, so that then as we find them, we can compare the two, work out what the difference is, and work out why there's a difference, and do some science. The way we do that is we actually look at the stars near the sun, because interstellar objects form around other stars. Their velocities and compositions are going to be correlated to those stars. So by looking at the stars and making assumptions about how things move through the galaxy and how planetesimals form and are ejected, we can then map that stellar population to our predicted ISO population. A fun thing about that is ISOs are rocks and balls of ice. They don't have any mechanism that removes them from the galactic population, whereas stars die. So we don't actually want to look at the current living stellar population. We actually want to work out what the stellar population would be if stars didn't die. Like, we need to account for the fact that some stars, about 10%, have actually been removed from the population. Turns out that population that we're trying to infer, no one's ever really talked about before. So that meant I got to name it, which was fun. And being an Oxfordian, I decided to name it the Sine Morte stellar population, which is Latin for without death.
There you go. Yes.
So we calculate this. We do this with the Gaia survey, which up until earlier this year was a spacecraft out orbiting the sun, and very accurately measuring the positions and velocities and other properties like composition, as measured by this metallicity and ages of stars. And from that population, we debias the survey and then account for stellar death, and that gives us this Sine Morte stellar population.
Very cool. I'm with you.
From the stars, we then need to go to the ISOs. So we make some assumptions about how ISOs form and they're ejected and move to the galaxy. We assume things like the number of ISOs produced by a given star is going to be proportional to the metal fraction of that star.
Fair.
Basically, ISOs are made from ices like water ice, H2O, carbon monoxide, ammonia, or dust. And by mass, these things are dominated by like the metals, the elements heavier than hydrogen, helium.
Uh-huh.
So we assume the more metals are in a star, the more ISO it's going to produce from its planetary system.
Makes
We
sense.
also assume that this ISOs are ejected fast enough to make them leave their planetary systems, but not actually so fast that it's going to massively affect their velocity distribution. We assume that the stars are going to have the same velocity distribution as the ISOs. So where there are peaks in the velocity distribution, where we can see in the stars, there's going to be peaks in the ISO distribution as well.
Okay. Yeah.
However, the ISOs are ejected fast enough that given a bit of time, they're actually going to disperse away from their parent stars.
Yes.
So we're only looking at stars near the Earth and near the solar system so that we can get a really accurate picture of what the population looks like exactly here.
Cool.
But those stars almost certainly aren't the parent stars of the ISOs that we see. The ISOs we see are billions of years old. They could have formed, as I said, on the other side of the galaxy, on a star that's now dead. So there's a slight subtlety to the assumptions there.
Yes.
But
you got to start somewhere, and these are pretty straightforward assumptions, right?
Yeah, it makes the maths a little bit easier. John, the co-author on this paper, is doing some very complicated maths to work out how ISOs actually move through the galaxy.
Okay.
And he has a really interesting paper on the kind of braided streams that they'll form there.
Yeah. Scattering will be quite different.
Actually, funny enough, the scattering isn't different.
Really?
Compared to the spiral arms and the GMCs that dominate the dynamics of these things, stars and ISOs are equally massless. So actually, part of this assumption is that they'll undergo the same scattering over time.
Cool.
Cool, yeah. So applying these assumptions, modifying the stellar population like this, gives us a population of ISOs. The properties we have for these are velocities and their ages from the stellar ages from Gaia and compositions. Because we know the metallicities of the stars and we have chemical models that tell us, given a certain stellar metallicity, what's the composition of ISOs it's going to form, what's the composition of planetasimals.
Okay, cool.
And the rough correlation there is that higher metallicity stars produce lower water mass fraction ISOs, more dust, less ices, and things like that.
Okay.
So this gives us our Ōtautahi Oxford model, this prediction of what the ISOs are going to look like as they fly through the solar system in their velocities, ages, and compositions. The stellar population from which these ISOs come from have interesting correlations between their velocities and their compositions and ages. Older stars are generally lower metallicity and have a wider spread in their velocities, whereas younger stars generally are more on circular orbits around the galaxy and higher metallicity. So that these same correlations we expect to see in the ISO population.
Okay, all right, I'm with you.
Cool. This is our model. This is more in detail in a previous paper we wrote, actually published earlier this year, so another Hopkins 2025. But that's where the details are if anyone's interested. We can now go to the next section, which is actually putting 3i in the context of this. Yeah, there we go.
Check that paper out. We'll put a link to it in the description below the video.
Oh, nice. Thanks.
There we go. Okay.
Oh, and there's John's paper on the streams.
Yes, there we go, which I'm going to have to read to find out more about scattering. So, okay.
Cool. We can go down to the next section, and that is actually looking at 3i. So this, as I said, this paper was written literally 3 days after it was discovered. So we didn't know much about it, but the first thing you get out of an interstellar object when it's first discovered is its velocity. The way that we know that it is an interstellar object is the fact that when we fit an orbit to it, it's strongly hyperbolic. It can't have come from within the solar system.
Yes.
And following that hyperbola back to the kind of straight line incoming section, that gives us a velocity relative to the galactic population. It gives us an orbit around the galaxy. And using this, we can plot it on some plots. So if you go down to figure 1,
Okay, let's go.
we can start to look at this.
Let's go figure 3-1. Here we go.
Hey, okay.
Yeah.
So top left is, so the gray in all of these in the background is the our prediction, the Ōtautahi Oxford model, what we think the interstellar object population is going to look like.
Cool.
Then all the pink lines and triangles are 1i, the green lines are 2i, and the orange ones are 3i, this new object. So just looking at the speed, all 3 ISOs lie very nicely within the most kind of probable region we think, which is nice. It means that we're not wrong yet.
Yeah, you're not out here.
But interestingly, 3i is fast. It's twice as fast as 1i and 2i. And you can see this on plots of its like trajectory through the galaxy, through the solar system. Sorry, it really zips through. The planets barely look like they're moving, that kind of time lapse.
Cool. Okay.
So this gives us the speed. It's fast. We can also, from this, its velocity is a vector, so we can look at the direction, and that is this radiant plot.
Yep.
Next one there. So this is an on-sky map. The shading gives you the likely directions we expect ISOs to come from.
Okay.
The coordinates are RA and DEC. So the equator, north and south. Most ISOs we expect to actually come from the northern hemisphere. There's this kind of concentration along the equator, but the rest, the tail, is all around coming from the north.
Yes.
Which is actually slightly bad news for the LSST survey, because that's a big survey about to start, which we'll talk a little bit about later.
Cool.
It's going to find more interstellar objects, but unfortunately, it's going to find a lot of them after they've already passed through the solar system, because the LSST mainly looks south, and most ISOs come from the north.
Okay.
But oh well, that's fine. 1i, 2i, again in pink and green, are mainly within this cloud. But you can actually start to see that 3i, in terms of the radiant, the orange triangle down there, is kind of outside the distribution, and that's interesting. The orange and blue lines here are the ecliptic and galactic planes as well, for anyone who thinks in slightly different coordinates.
And what is the yellow square?
And the yellow square is the solar apex, so the direction that the sun is moving in. That actually is a useful point to make, because that's why there's a big cluster of ISOs coming from that direction. The sun actually moves pretty fast relative to local stars, so it's actually running over a lot of ISOs.
Okay. Yes. Okay. I'm with you. Cool.
3i, though, looks kind of outside of this distribution, and that's interesting. So if we go down to the bottom left plot,
yes, there's a speed
we can now
direction. Ooh, okay.
So we can now start to look at the components of the velocity. Okay. So U and V are the components of velocity within the galactic plane. U points towards the galactic center, V points around the galaxy. And there's some really interesting structure here. So the ISO distribution has these kind of waves, these overdensities and underdensities.
Bands.
These are actually known about in the stellar population. We've known about them for about 25 years. They come from orbital resonances. So stars that go around, as they go around the galaxy, if their orbital period has a like low integer ratio with the orbital period, so the rotation period of the spiral arms, you can end up with favored or disfavored orbits. And so these spiral arms shift stars' orbits around, so that in the solar neighborhood, the velocity distribution has this interesting pattern.
Indeed. Cool.
The yellow again is now this is the sun's velocity. Sorry, no, that's the local standard rest. The sun's velocity is 0, 0. Everything's relative to the sun here. So that's kind of a middle average velocity, roughly. It's kind of made up, but a useful point of reference.
Yes.
1i, 2i, 3i again in the triangles here. We've managed to lose the legend, but pink 1i, green is 2i, orange is 3i.
Yes.
1i and 2i look like they're very firmly within these overdensities where we expect to find ISOs. and
Yeah.
that's good.
Yeah.
Um, these overdensities in the stellar population are also stars generally which have higher metallicities, so they're even more pronounced in the ISO distribution because we expect more ISOs to be coming from stars of higher metallicity, which are generally found in these overdensities.
Nice.
So it's good that the
Hang
first
together.
two, yeah, it's good the first two seem to be coming from where we expect. 3i again, though, is kind of on the outskirts of this distribution. It doesn't look like it's quite inside that overdensity. And it really becomes clear when you now look at the third component of velocity, the outer plane down the bottom right.
Yep.
Oh, yeah, yeah. So
Okay.
this
Oh
W
yeah. Uh-huh.
is the vertical velocity out of the plane of the galaxy,
Mm-hmm.
and it really sticks up out above the bulk of stars where we expect the bulk of ISOs where we expect them to be. This means that its orbit around the galaxy isn't just going kind of around in a circle in the disk, it's kind of hopping up and down like a dolphin in the water
There
as
we
it goes round.
Uh-huh. Mm-hmm.
And when I saw this, I got interested because we know that stars that do this are generally older, they're generally lower metallicity,
Yes.
which is interesting. Suddenly, our nice picture of the first two ISOs coming from high metallicity stars in the place in the velocity space where we think that they come from. Suddenly, 3i doesn't actually seem to quite follow this, which is interesting.
Yeah. 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 They're picking up a different population. Mm-hmm.
Yeah.
Cool.
Um, also, if the stars that have these kind of orbits are generally older, that might mean that 3i is generally older. So that was where we next went with the investigation.
Yes.
And I think that's probably the next section.
Yes. Age and age velocity dispersions. And I'm gonna blow up figure two, zoom in a little bit
Yeah.
so we can see it all.
Actually, I think skipping down to the graph, we managed to skip a section,
Oh, no.
which is figure two.
Yeah, no, figure two. Uh-huh.
Hey, yeah.
Yeah, yeah.
So, first of all, though, we look at our Ōtautahi Oxford model is a list of stars basically with different weights and different properties. The weights then are what maps it to the ISO population.
Okay.
So we can,
Okay.
and I mentioned that these stars have correlations at certain velocities. Stars are generally higher metallicity, younger, or low metallicity and older generally. So we can, with just the velocities of the ISOs, we can try and make inferences about the populations of stars that they came from
Okay.
by looking at similar stars with a similar velocity anyway, and the properties of those stars.
Okay.
So that's what these plots in figure two are.
Mhm.
Again, in the background gray is the overall Ōtautahi Oxford model. If we look at the first plot, this is metallicity. So generally, metallicities of these stars are peaked around zero with a bit of spread.
Yes.
But then what we can do is zoom in and focus just on the stars that have a similar velocity within 5 kilometers a second
Okay.
of 1i, 2i, and 3i,
Okay.
and try and make inferences about the stellar populations that these objects came from.
Okay.
So 1i and 2i, again in pink and green,
Yes.
seem to be shifted towards higher metallicities here. Relative to the overall sample in gray,
A little bit. Yes.
yeah, it's very noisy, which is why we've had to add these error bars on, but there's definitely a shift towards these higher metallicities for 1i, 2i. And
Right
that makes sense.
there.
We saw them in the overdensities and the
Right
velocity
there.
dispersion,
Okay.
in the velocity distribution. Yeah, it's noisy, and we'll get to that. But generally, 1i and 2i seem to be higher metallicity as we thought. That's cool. 3i, on the other hand, is shifted the other way. It's more on the low metallicity side.
Yes.
Again, it's kind of slight, but there's definitely a leaning towards the low metallicities.
Indeed. Indeed. I see it. Yep. Mm-hmm.
This has an effect on the compositions. So there's this correlation between the metallicity of a star and the water mass fraction of the ISOs that it'll produce. So
Go.
this is this middle plot. Again, in gray is the background population, pink for 1i, green for 2i, orange for 3i.
Yep.
And similarly, 1i and 2i are generally shifted to lower water mass fractions. We expect them to be dustier, probably, whereas 2i, 3i are, 3i, more shifted towards the middle ground, not in the very low water mass fraction, they're more in the middle.
Right. And what is the y-axis? What is p here?
The probability distribution.
Probability. Okay. I'm good.
It normalizes to one, but because it's a fraction, there are no units, and that actually makes things
I'm
a little difficult to understand.
I'm good. I understand it now. Hmm.
Finally, we can look at the ages.
Okay.
So one eye, two eye. Uh, Actually, the main takeaway from this plot is that estimating the age of an object just from its velocity is very difficult. Um, the original point of this was because a lot of people have claimed that one eye is incredibly young just from its velocity,
Yeah.
and there's a this the doing single kind of point estimates with wide statistical distributions is generally a bad idea.
Generally.
In reality, the distribution of ages at a given velocity is wide almost all the time. So
Yeah.
that was this part. All of these histograms go from 0 to 14. There isn't really much that you can tell about the age in
Yeah.
this way, anyway. Start to run into a problem here, and that's that Gaia's age estimates are very noisy, and because we're only looking at a very restricted sample of the stars which have
Right.
similar velocity to 1i, 2i, 3i, that makes it even noisier. These error bars are so big that these histograms are pretty much all statistically indistinguishable.
Right. Right. Okay.
But I did want to have a further look at the ages of
Okay.
these objects and of 3i. So we actually turned to a different method then for this next
Okay.
section. Um, so here it's when I talk about the previous methods and the point estimates. There's a correlation between the stars' velocity distributions and ages, as I said before, where the older a star is, older populations of stars generally have wider spreads in their velocities. And this is called the age velocity dispersion relation, or the
Uh-huh.
AVR.
AVR.
If you do a point estimate and equate the width of this velocity distribution to the velocity of an object, that's when you get these statistical problems and an absurdly young one eye.
Okay.
So I want to do this properly with some nice Bayesian statistics.
There you go.
We've got a statistical relation between the velocity distribution at a given age. So we can use Bayesian statistics to invert that and say for a given velocity, what's the distribution of ages that this object is likely to have? What's the posterior distribution?
Cool. Okay.
And when you plot that for 3i, that is figure 3, which is up here.
Mm-hmm.
Again, it's a very wide distribution. There is absolutely no way that we can say for certainty that 3i is one fixed age just in its velocity. And that's the same for all objects.
Yeah.
But there's a very strong leaning towards old objects here.
Yes.
We plot in groups. So the blue line is the overall posterior. Again, it normalizes to 1.
Yes.
The green confidence is a confidence interval for 68%.
Okay.
All very much in this old age section from 7.6 gig years onwards.
Yes.
The solar system is 4.5 gig years old.
Yes. Yes.
Therefore, 3i, the tagline of this article is 3i is probably the oldest object, the oldest comet we've ever seen.
Cool.
The star it formed around might well be long dead if it's the age of I think the sun's overall lifetime is 10 gig years. So reasonable chance that if it formed around a sun-like star, that star's gone. And all that remains of its system are the ISOs that we see flying through our solar system.
That is awesome.
It's really cool. I said you can do this for all the objects, and we do it for 1i and 2i in the appendix down below. Can we put down there?
Yeah, let's slide down to Appendix 5 since you do it for 3i. Let's take a look at 1i and 2i. And
yeah.
Mm-hmm.
Again, the point here that I wanted to make was that you can't get a point estimate. You can't exactly say what the age is. All of these have really wide confidence intervals. But 1i and 2i both seem to be skewed towards younger ages, which is what we thought.
Consistent with velocities, yeah.
Yeah, 1i being the youngest of the three, but it's still 68% chance that it's like less than 7 gig years.
Yeah.
the red dotted lines here are what you get from the point estimates.
Yes.
And I just wanted to show how easy it is to massively underestimate what's actually going on here.
Yes.
Point estimates underestimate ages, but the full confidence interval shows that generally younger, but still massive uncertainty, very wide confidence intervals.
Okay, we'll come back to that. We'll come back to
Cool.
that. Very cool. Okay, so that's 1I, 2I. Let's go back to 3I.
Yeah.
Right.
So all of that is things that we've inferred from 3i, its properties, just based on its velocity. For the rest of the article, we look at a couple of other things that we can do. This next section is using John's maths of he spent a lot of time modeling the streams of ISOs as they come off a star. They form these like tidal streams that stretch out and wrap around the galaxy.
Okay.
And his paper shows that there's a chance that we'll actually get two objects from the same stream at some point, and we'll be able to tell from the velocities. Probably these two objects from the same stream will have very similar velocities, and the velocities will be closer than you'd statistically expect from a random sample of all the stars.
Okay.
So here he does that maths to work out, okay, we've got three, what's the probability that two of them are from the same stream?
Fair.
And again, there's some more Bayesian statistics here of probability of related given some of the parameters of the streams. I think it's the velocity of 3i, and the streams have a parameter that's like the width of them, how much scatter is in the velocities, how wide are they as they move through the galaxy.
Yes.
And he does the maths. Then again, the details are in his 2025 paper down there. And works out. I think the next graph is the killer result.
Okay, so let's pull the crank on that.
Yeah.
And we get the Bayesian on velocity and sigma. Okay.
Okay. So changing this parameter of the width of the stream, what's the probability that they're related? And the numbers are generally quite low. It really shows it down in the lower plot, actually, where how close would their velocities have to be in order for the probability of the being, let me get this right around.
Okay.
I think the black line is the probability distribution of the velocity separation, assuming that they're not related at all.
Right.
And
okay.
In order to statistically say, well, they're probably are related, you'll need very low velocity separation. So you'll need to be kind of down actually beyond where the I'm getting my Bayesian and my frequentist stuff mixed up here. I think this is like a frequentist H0, the null hypothesis is the black distribution. If they weren't related at all, what would the velocity separations be?
Okay.
And to argue that you have to reject H0, you need very low velocity separations of the three ISOs. So down kind of on the very lower end, outside of this distribution that John's worked out. And all these velocity separations are pretty much slap bang in the middle of the expected distribution if they aren't related. So the conclusion is so far these three probably aren't from the same stream.
Right.
But that matches up with John's predictions in his paper.
Cool. Very cool. I'm with you.
Yeah. Next, we look at the orbit. So in a previous work, me and Rosemary looked at what's the population of ISOs going to look like as seen by the LSST. So what ISOs is it going to find in terms of its their orbital properties, their size distributions and stuff like that. And we found that 3i kind of looked slightly odd in that distribution. Somewhere there's a number of one of its orbital parameters. I think the argument of perihelion was quite outside of the distribution that we expected to see for the LSST. And we're still ongoing investigating that and trying to work out did we just get lucky or unlucky there, or it could well be some difference between the Atlas survey, which found 3i, and the LSST survey, which we modeled in our previous paper.
Okay.
That might explain the difference, but we're still investigating that, and we point that out here.
Cool. Okay.
The other interesting thing to point that we looked at here is the uh, abundance of objects like 3i. So
Oh,
we know roughly how much space the Atlas survey has scanned, and we know we found one 3i-like object in
oh
that
yeah, yeah.
space.
Okay, okay. Go ahead. Yes, I'm with you.
And that gives us then the abundance of how many things like it are there. And it's complicated by the fact that 3i is a comet, so it changes brightness in an unpredictable way. But order of magnitude, we can say that 3i-ish objects are, I think, about a factor of 1,000 less likely than 1i-like objects,
Okay.
Oumuamua,
Okay.
which makes sense. Oumuamua is a lot smaller, so there can be a lot more of them
Right.
in space without us seeing them so often.
Right.
3 objects are bigger. We've got kind of a few
Okay.
kilometers. Our current understanding of what the radius probably is, whereas 1i was right down at 200 meters in radius or
Very
diameter.
cool.
So
Okay.
yeah, um, that is everything that we could work out about 3i in 3 days.
2 days, yes, very good. Well, we will come back to this in a minute. Very cool. Very cool. Matthew, I want to thank you so much for sharing your beautiful 3-day article with us. That's just really awesome. Very cool. And let's see, you touched on it several times, and of course, it's been a little longer for the publication process than it was for the writing process. So let me ask on where do you think we go from here, given the published article and the intervening time? Sort of what's next?
So in terms of 3i, currently it is behind the sun. It's so we can't get any data on it currently. We're looking back over at the data we've gotten it before
Yes.
it disappeared, and preparing for when it does reemerge. The comets evolve as they move through the solar system. Their outer layers sublimate first, and the outer layer of 3i may have been affected by cosmic rays. So there's an idea that after it passes the sun and we've seen it more developed, we'll actually be sampling the kind of inner layers that are sublimating rather than
Oh,
like
right,
the outer crust.
right.
So we might get a better handle on what its overall bulk composition is.
Cool.
I'm currently working on predictions for how more detailed chemical models, instead of just looking at the stellar metallicity and how that affects the water mass fraction, look at
Uh-huh.
more stellar properties and how that looks kind of affects different chemical compositions like carbon monoxide or ammonia.
Okay.
So I'm hoping to get those predictions out around the same time that 3i pops out, and we'll do some fun science there.
Yes, very cool.
As for the community and ISOs as a whole, I mentioned it a couple of times. The LSST survey from
Uh-huh.
the Vera C. Rubin Observatory in Chile is going to start later this year. It has been long anticipated, and
Yes.
it's going to find a lot more ISOs. We've got 3 so far, but mine and Rosemary's predictions say that it might even be finding one every few months,
Wow.
which is would be absolutely fantastic. I did my entire PhD with 2 objects, and now we're going to get one every few months, and that's going to be brilliant.
Very cool. Very cool. That will be very awesome to have. Nice. Will be really exciting to see both A, 3i, how it develops and what we can pick up from it, and B, the anticipated future where we have dozens and dozens of these things. It'll be
Now
absolutely
wait.
very cool. Very exciting future.
Thank
That's for sure. Very cool. Matthew, thank you so much once again for sharing your very awesome article.
you very much for having me.
And that'll do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye bye.